Alright, so let's wrap up complex experimental designs by talking just a little bit more about how to think about and create figures, because sometimes this can be a little bit on the confusing side. So, how do you actually graph results when you have them? I mean, you know a little bit about this from making your bar charts for your t-tests and your ANOVAs, but for interactions, it can be a little bit more complicated. Instead of graphing main effects, of course, you are trying to tell people something about interactions. So instead of plotting the grand means for an entire condition, you're plotting the cell means for specific crossed conditions. So not everybody in the exclusive dating condition, but people in the exclusive dating condition who also had the person attracted to them versus people in the exclusive dating condition versus people attracted to their friend, for example. So you're plotting the cell means, not the grand means of conditions. Just like always, you always want to have the dV on your y-axis, the vertical axis, and you first place one independent variable on the x-axis, those different conditions occupying different space there on that horizontal axis, and then you plot the other IV by different lines on the graph. Sometimes people will still use bar charts for ANOVAs for these interactions that people are trying to understand, but frequently it's a little more straightforward to use lines. Though sometimes if you want to show like standard errors in a particular way, it can be easier to use bar charts or histograms, but frequently people tend to prefer line graphs, so that's what I'll talk about here today. If you have more than two independent variables, you can't really add another dimension to your graph. It would have to be, like three-dimensional or something to add a third independent variable. So generally what people do is they either choose the conditions that are more important or they make two graphs separately. So if you had this design from Bazzini and Schaefer and you had another condition, well, you'd have to have two separate graphs showing the scenario by dating status interaction in each of those separate conditions. So it gets a little bit more complicated than a 2x2 design with a one-way or a two-way interaction. So how do you interpret graphs once you have some of that information there? You can look at main effects in a way that I'll describe here verbally, and then I'll move on to talk about it by showing you specifically on a particular figure. But the way that you would want to do this in a graph, and remember these are just estimates, you can't really be exact with this, but you can get an idea of what the main effects are like. On those lines, for those conditions, you estimate the midpoint on those lines and compare them. And if one is higher than the other on the y-axis, then there's probably some kind of main effect. For the x-axis variable, you again estimate midpoints, but between the lines within each condition. And again, if the x-axis height is much different, then there's probably a main effect. And we've talked a little bit about interactions already. How to interpret them there. If the lines are parallel, then there seems to be just kind of a main effect and not an interaction. But if they are crossing or converging, then that is going to be an indication that the interaction is significant and it is meaningful to interpret. But when you are looking at these types of graphs and trying to interpret things, you don't want to jump to conclusions based on just a visual representation. You need to complement these things with statistics generally. So let's just go through one example quick. Just some data from a study that had to do with predictors of poor mental health and relationships. So here I have plotted on the y-axis the number of days of poor mental health people reported. On the y-axis we have the x-axis, our first independent variable, if the participant has ever been divorced or separated, and the lines are the other independent variable, male and female participants. So there's three things we can estimate here. We can estimate the main effect for divorced or separated, the main effect for respondent sex, and the interaction. So to look at the main effect of respondent sex, let's start with the lines. There are lines here that have both conditions within the male participants and both conditions within the female participants. So assuming the sample sizes in each are relatively similar, the midpoint of this line here, that's around 3.7, is probably where the mean overall for males are. And up here, maybe around 4.1 or 4.2, is probably where the mean for females is. So 3.7 to 4.1 or 2, it's hard to really tell. Maybe there is a main effect. Along the whole line, female is above male, but we don't know how big the standard errors are, but we can have some expectation that there's maybe some small effect here. For the other independent variable, divorced versus separated, here are all the divorced or separated people, and here are all the people that have not been. So the midpoint here for all the divorced and separated people is probably somewhere in the 4.7 range around here, and for people who have not, it's somewhere in the 3 range down here. So these seem to be pretty significant differences, right? The main effect of this whole condition compared to this whole condition here. The interaction, though, we might look at and notice that, it does look like these lines would cross eventually, right? They're kind of coming to a point. There is maybe kind of a mouth there, or a sideways V or something like that to, remind you of what shape you're looking for. But again, it's a little bit unclear. This is a situation in which we see this and it doesn't seem like a slam dunk. Maybe, we definitely would want to rely on statistics to tell us like we would always, but in this case, it's especially hard to tell. Okay, another representation or another example I think is useful is to think about this one too. It's again mental health days in the past 30 days, and it's again another data set with respondent sex and have you ever been divorced or separated. But you notice that they're different. Over here I have respondent sex on the x-axis and have you ever been divorced or separated on the lines. So for these, you can estimate the midpoint for people who have not been divorced or separated down here in maybe the 2 range, compared to people that have up here in the 4.7 range or something like that. Pretty big difference. For male versus female participants, it's probably in the 3.7 range for male, and maybe the 3.9 range for female or something. So, maybe there's not a difference here. And for the interaction, maybe these lines look pretty parallel. Maybe they feel like way off in the distance they'd cross. It's, again, kind of hard to tell for this interaction. When I do this part in class, we talk much more about this, and I ask people to kind of reflect on what things about each of these pictures indicates, something about an interaction or a main effect, and which one's easier to interpret or understand. And the reason I do that is because these are actually the same data points, just plotted in different ways. So I try to be a little tricky about that and show people that it really matters how you plot data. These data points are actually the same 4 data points, just plotted with one on the x-axis in one scenario and one with lines, and then flipped for the other one. So this is just an example of how when you have kind of ambiguous data, it can look a little bit different and kind of mess with your interpretation depending on how you choose to present it. So you want to try to present it in the way that's clearest to people, but you also don't want to try to mislead people and just pick one that makes it seem like there's some kind of big impressive effect or something. You want to do it in a way that helps you actually explain something meaningful about your data and make sure that it is clear as possible to people. So for this one, if you actually ran an ANOVA with an interaction to see if there was an interaction there, we have divorce status, sex of respondent, and then here that product of the 2 multiplied together, obviously, so we can see if there is an interaction. The F value here, very, very low, not even close to 0.05 significance level for us. So maybe it has something to do with the sample size or how big the errors are, because the errors here are enormous compared to the effects that we're seeing. So it doesn't seem like this is significant, clearly. One other thing I forgot to mention about this too is that these estimated marginal means, this is just like estimating a cell mean, basically. But remember that your DV here is poor mental health days in the past 30 days, and your DV on the y-axis only goes from 2.5 to 5. I just want to mention this because it's really important to be very clear and transparent about why you're choosing the ranges you are on your graphs. Like, when your scale really should range from somewhere down here to way, way past the top of the screen, and this is all you have, then it can seem a little misleading sometimes. You should try the best you can to include, the entire range of your data. And, there probably weren't very many people that were reporting close to 30 poor mental health days in the sample if the means are so low. But, it's a little misleading to really just show only up to 5. That's only a sixth of your scale. And maybe it doesn't tell us the whole story. So whenever you look at any figures, just try to be aware of what scale people are using on their axes, so you're not being misled. For example, sometimes you'll see 7-point scale dependent variables represented, and it's like 4.2 to 4.4 or something. And who cares if there's some kind of interesting looking difference within that tiny spot? If it isn't really making any movement along the scale, then it can be a little bit misleading to talk about it that way. Okay, one other one, just to show you what it would look like if you did have a pretty clearly significant interaction. This is poor physical health days, and it's whether people have been widowed and crossed by their sex. So male and female as the sex conditions on the x-axis, and have they been widowed as the 2 lines. And this is, pretty clear, right? They're crossing. It seems like there is, not much of an effect for respondent sex for people that have not been widowed, but there's a big difference for respondent sex for people that have been widowed, such that men have many more reported poor physical health days than women. If you want to look at the main effects too, there doesn't seem like there really would be that big of a main effect for have you ever been widowed, because the mean for no is probably around here. The mean for yes is probably about right here. It's maybe only 3/4 of a day difference or something like that. But we still can tell that in one condition, the yes, I've been widowed condition, matters a whole lot if you are male or female, even though it doesn't matter at all for the no condition. So this is another one of those scenarios where it's really important to look at the interaction to tell how these variables are influencing one another. And if you plotted this the other way, this way you have a real x as your figure. You can plot it a different way, so it looks more like a V or Pac-Man thing. But again, pretty clear interaction that have you ever been widowed? It does make some kind of difference for both sexes. But it does seem that men overall are having more poor physical health days regardless of if they've been widowed. So that main effect of sex is a little clearer on this figure that graphs it this way. But if you went and did an ANOVA and you tested that interaction, you'd see the product here, respondent sex by widowed status. There is significant F value, less than 0.05, which, as we know, doesn't totally mean everything all the time, but gives us an indication that this probably isn't due to chance. So there is a significant interaction in that one. One last thing that I'll mention, when you have most of the things I've been talking about here, or all of them rather, have been scenarios where you only have 2 different conditions. But of course, as some of you encountered in your studies, sometimes your variables have 3 conditions, or 4 or 5 or 6, So if you have more than 2 conditions in one of your variables, you want to select the one that has fewer levels to be plotted as lines. So if you plot all these different lines, it can be really difficult for people to interpret, exactly what these differences mean. But if you have fewer lines, then it's a little bit easier to identify these trends. So these are the same data sets plotted in 2 different ways. This one tends to be a little bit busy and not what people prefer to see. It kind of goes against APA style. And if you have fewer lines, then the trends that you see just tend to be a little bit clearer. This isn't, a hard and fast rule that should always be followed every single time. You should think about the story you're telling and how your data are best represented, but it's again kind of a soft rule that might help you figure things out. All right, that's it for complex experimental designs. I will be back Wednesday with some discussion of publication and getting into things about the reproducibility and replicability crises that you started reading and watching about last Friday. All right, thank you.